Okay, hello everyone, and welcome to lecture 12. In this lecture, we discuss optimized training of large language models. In this part, I will be presenting the part related to maximizing the GPU utilization for efficient and scalable training. Now, why are we doing this? Well, first of all, we're still seeing a lot of improvements with training bigger models, bigger language models. And as of right now, current GPUs cannot train more than like 1.4 billion parameters in one GPU. So how do we achieve bigger models on multiple GPUs? How can we divide them? And this is going to be the main topic of this presentation today. We cannot just throw a lot of GPUs at the problem and think that it's going to be solved. Hopefully, after this presentation, you will appreciate the engineering put into it. So a little bit of an ambitious outline here, but we're going to be talking about parallelism primitives. So we're going to be talking about data parallelism, pipeline parallelism, model parallelism, and then finally the zero optimizer. And we're going to be also talking about some necessary optimizations for these things to work, like activation checkpointing and mixed precision training. So first, let's just talk about data parallelism. What is data parallelism? Data parallelism is the first straightforward implementation of some form of parallelism over multiple GPUs. So the idea is, given a mini batch, you distribute it over multiple, so you split the mini batch into multiple micro batches for every GPU, and basically every GPU has a copy of the model. Now every GPU does a forward pass, backward pass, computes the gradients, and then they can aggregate these gradients together, either using a parameter server, could be another GPU, or they do some form of auto-reduce operation, and by this way they reduce all the gradients together, and then they broadcast the updated model to all of them, and then they go on to the next mini batch. The good thing about this is that you get immediately, so for these three GPUs, you get 3x extra throughput, and there is no design that you need to do. So enter pipeline parallelism. It was introduced in gpipe and pipedream, and the idea is, instead of having the model copied in every GPU, you have interlayer splitting. So you split the model, so the first layer is on the first GPU, the second layer is on the second GPU, the third layer is on the third GPU, and so on. And so hopefully every layer will have 1 over the number of devices of the weights, so it will have less memory. And you just pass the mini batch, you split it into also 3 micro batches, and you pass them in sequence in a pipeline. But the naive way to do this will not work, because if you just make the forward through the first layer, then the forward, the second layer, third layer, fourth layer, and then you go backward in each of them, basically you're having the performance of one GPU. And all of the white blocks here are idle or bubbles. So how can we optimize that? Well, this is the idea behind gpipe. the idea is while the first batch does forward, then after that the next batch goes in, like in a pipeline way, and then the third batch goes in, and then the fourth batch. And the idea is that we want to maximize the number of these full-length columns, because at these full-length columns is when the pipeline is completely utilized, and this is the maximum utilization that we want. So this is an extensive example of this idea in motion. So we have 8 micro batches. We will interleave them forward and backward in the following way. The moment the first batch finishes, the second batch goes on, and so on. So for the first layer, second layer, third layer, fourth layer, and then you do the backwards for each of them. And essentially, this is what you have. You have more full-length columns, and so you have higher throughput and more utilization. If we want to analyze this more formally, we look at the bubble time per mini batch. So the bubble time is the number of devices minus 1 times the forward plus backward time, which is essentially the time that it takes for a mini batch to fully enter through the pipeline and to fully withdraw. Ideally, we want to be using so M here is the number of micro batches. So we want the ideal time is to be M times TF plus TB. So the efficiency that we get out of that is, well, if you do the calculation, it's 1 minus K minus 1 over M. And in GPipe, they find that empirically for almost linear scaling, you need the number of micro batches to be bigger than or equal 4 times the number of devices. And if you plug in this in our analysis here, we get that it's effectively 75% scaling efficiency, which is good enough. And if you increase M more than that, well, you get higher efficiency. And, well, pipeline parallelism reduces the memory proportional to the number of pipeline stages. So it allows the model size to scale linearly with the number of workers. And it has the lowest communication volume. However, it cannot scale indefinitely, because increasing the pipeline size decreases the computation per pipeline stage. And it needs loads balancing. It is architecture independent, but it does need a little bit of code rewriting. And the memory per device, it's going to be the maximum partition, so like the maximum width of layer, plus the activations for all the micro batches, because they are stored as we are going. Enter the next parallelism idea, which is to split it the other way. Instead of splitting it layer by layer, you split the layer itself horizontally. So we split this first layer here, we split these two things, we split them, and so on. And the idea is that we're computing every layer in parallel, okay? And since this really requires us to go into the depth of implementation of these blocks, we're only going to be focusing on the transformer block, which is exactly what the paper Megatron did. So, what is the main component in training large language models? It's basically matrix multiplication. So we are focusing on generalized matrix multiplication here. And in the paper, they introduced 2 forms of parallelism: column parallelism and row parallelism. Okay, so in column parallelism, so you're multiplying x times a, and you want to do this on 2 devices. So what you do is you split a by column. So you put the first column here, and you put the second column here. and then you replicate x on both devices, and then you do the multiplication. Now, when you do the multiplication, this output is going to be the first column of the output, and this output is going to be the second column of the output, and you just want to concatenate them. Okay? For row parallelism, however, instead of splitting A by column, you split it by rows. So you send the top to the first device and the bottom to the second device, and you also split X by column this time. So you put the left side on the first device and the right side on the second device. And when you do the multiplication, now the output is going to be a partial sum of the final output. So it's like this entry should be all of this times all of this. The first device is going to be computing this times this, so it's going to be here, x11, x12, a11, a21. When you multiply this and this, you get y1 of 1, 1. In order to get the rest of it, the second device needs to compute this times this, which is going to be here. Then the output is going to be here. And the idea here, the costly thing you need to do is you need to sum these up. And summing across devices means that there is some form of communication that needs to happen. Concatenation, you can do the concatenation logically. There doesn't have to be like communication between them. You can just think of the tensor as existing on two machines but being split. While here, you cannot think of it like that. You have to add them. So, how does this apply into the transformer? Same idea can apply to the self-attention block, except that we basically will parallelize attention heads now. So let's assume for the sake of example that we have only two attention heads. We're going to put every attention head on a separate device. The first device is going to take, again, column parallelism. We're going to take X and we're going to split the V, Q, and K by column. And then we're going to do the attention, and then we use the row parallelism in order to complete the linear layer at the end of the self-attention. That's basically it. That's how you parallelize a transformer block horizontally. In summary, basically you have two all reduce operations, one for forward, one for backward for the attention block, and you have the same thing for the model parallel block. So they are in total 4 all reduce operations, which is a lot. So this idea of parallelism is essentially very expensive in terms of communication cost. So the results of that from the paper is that, well, you can, first of all, you can compose it with data parallelism. So model parallel on its own has like 77% scaling efficiency. So at 8 GPUs, each, instead of getting 8x the performance, you get 77% times 8x of the performance. But if you combine that with data parallel, you get 74% at 512 of GPUs, which is like a lot. That gives you basically a very high throughput that you can use for training larger and larger language models. But as we said, it's the highest communication volume, but it has the highest memory efficiency because we really split the computation across devices. However, it reduces the granularity of the computation while also increasing the communication overhead, which makes it not very good in cases where it would be across multiple devices. So if you were using GPUs from multiple devices, there becomes a communication bottleneck. So usually we just use model parallelism on GPUs inside the same like node or like server, for example. Other details is that it actually parallelizes the embedding layer and the loss layer, and the idea is the same. Basically, we use the parallel GMM and masking, and because it is bad across internode GPUs, to scale higher, we use data parallel or model pipelining. Like we compose it with other parallelism primitives. So in summary, we can split the data and not the model. We can just send the data to multiple devices and keep the model existing on every device and do the training. That is very fast. We can split the model horizontally, so every layer is a split, and we can give it the whole batch at once. That is very communication intensive, but the lowest memory footprint. And we can split it vertically like this and feed the batches to it sequentially. And that is the highest memory efficiency. That is also very high memory efficiency and the lowest communication bottleneck. So can we combine them together? Can we get the best of 3 worlds in that case? And the answer is yes, actually. You can think of each of these as a device, and you can abstract it and subdivide it in these ways. And this is actually what 3D parallelism is. So you take your batch and you split it into micro batches. Each micro batch goes into a data parallel slice. The data parallel slice basically consists of the whole model, but the model itself is split sequentially into 3 stages in that case. They are pipeline parallelism blocks, like we described them earlier. And each one of these pipeline parallel blocks is split into, for example, 2 model parallel blocks or tensor parallel blocks, such that you can have parallelism at the level of the tensor itself. And because this is the inner level, it's good for communication purposes, and this is good for efficiency purposes, and this is good for scaling purposes. So mixing them all together gives you the highest achievable parallelism you can get with the current technology. And this is actually the state of the art right now. So this is the model for Bloom, for example. It allows, so this is like 384 GPUs. It's like insane. You get 8 copies of the model, trained on a total of 384 GPUs. So you get 8 copies. This is the data parallelism. And each copy is divided into 12 pipeline parallelism steps. So like this is the sequence of steps. And then each pipeline step is divided into 4 model parallel steps. So one full copy takes 48 GPUs times 8 to get 384. Amazing. Okay, now let's talk about mixed precision training. Mixed precision training is basically the idea that allows us to train in smaller precision than 32 bits. Because 32 bits like is actually, this paper shows that it is not necessary to train in 32 bits. You need to keep the original weights in 32 bits because the gradient times the learning rate is sometimes too small, but the memory is dominated by the activations. So it's okay to keep the original weight in 32 bits and actually convert every single thing else into 16 bits, and you will get very close accuracy. There's a couple of nitpicks to this, which is in FP16, a lot. So basically, part of the gradient that is here, this part is like in the subnormalized range, so it's not representable in FP16, and it becomes 0. So the way you do it is actually you just scale the loss, because this is the important part. So you scale the loss a little bit depending on the kind of model you're using. So you move this part that becomes 0 in FP16 from this red line to this orange line by scaling all the gradients. And the easiest way to scale all the gradients is to just scale the loss. You multiply the loss by like 2 power 4 here. And in other situations, it's 2 power 8 or 2 power 16, depending, no, 2 power 8 or 2 power 10. And you get basically essentially actually the same accuracy. So you get the same exact model as if you did it in 32 bits. And in some situations, it's actually slightly a little bit more accurate. And I think it's just because like some regularization effect that happens when you're training in 16 bits. It's like the model generalizes a little bit better. So in summary, FP16 is faster than FP32 anyway, so we prefer that, and it takes less memory. We divide the memory by approximately 2. So that is good. We definitely want to incorporate that. And most of the papers that came after this paper in training large language models, they utilize this mixed precision training. They also utilize activation checkpointing, which is a very simple idea actually. So usually when you're training a model, you keep the forward states. So you train a model, you do forwards, you keep all the forward states with you, and then after you do the forward, you compute the loss, and when you're doing the loss, you start going backward, and when you're going backward, you compute the backward gradient from the saved state and the backward gradient that is coming. So you back propagate here, and then you go here, you get this state, and this, you go back propagate, and so on. But you don't need to keep all of these states in memory. In fact, you can keep only square root of them. So like you can do 1 and skip 3 and 1 and skip 3. And every time you're doing backward, you recompute from the last checkpoint. That is why it's called checkpointing. So from this checkpoint, it starts automatically when you start going backwards. So it does some forward for you and gives you this so that it's ready for back propagating. And when you do that, it triggers this one to start computing too. So when it starts going forward, it can meet you somewhere in the middle. So you're not really waiting for it. You can just spend a little bit of extra compute for the sake of reducing the memory tremendously. In the case of doing it actually every square root steps, you get square root of n memory reduction at the expense of like 1 extra forward per mini batch. It's like 33% of the computation increase, at least in the case of a transformer. Which is very, 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 very good. And now we go to zero. Zero is a zero redundancy optimizer. It is from Microsoft. It's basically an optimizer that uses most of the things that we talked about so far, and it does them in a clever way that makes the memory consumption basically amortized to like being actually divided by the number of devices, like the original memory consumption divided by the number of devices. Right away, like from 120 gigabytes, you go down to 1.9 gigabytes. Insane. So how does it go? It goes essentially like this. So first of all, how much memory does the model take? Well, it takes for every parameter, it takes 2 bytes, like FP16. So it takes 2 bytes for the parameters, 2 bytes for the gradients, and then there are some optimizer states, which, because these optimizer states are like in 32 bits, they are 4 plus 4 plus 4 bytes, so they are actually 12 here. And then you multiply it by the number of parameters, this is what you get. So there are 3 levels of parallelism that zero does. The first one is optimizer state parallelism, and then optimizer state plus gradient parallelism, and then optimizer state plus gradient plus parameter parallelism. And in here we can see the speed up of zero being very high. We can see that well, the throughput per GPU, it's like consistent. It only starts to go down in like very high model parameters, but the speed up is really high. And the speed up becomes really significant when the model can no longer fit on a single node. So in here, the baseline is model parallelism on a single device, where you can see like they are relatively close. But after this point, it can no longer fit on a single node. So you need to have inter-node model parallelism in order to fit it. This is where the throughput per GPU goes down really fast. And this is where zero optimizer really shines, because it scales so much better in high parameter situations. Okay, so here we see an example of zero on 4 devices. Each device has a portion of the model. So device 1 has this portion, and so on. And then in the forward batch, each party corresponding to a certain section of the model, it sends it to all the clients so that they can do the forward on their respective data. So this is a form of data parallel combined with pipeline parallel. The forward then gets computed with the loss. When you're doing the backward loss in your part of the data, in your part of the model, all the parties give you the gradient for this part of the model. And so the communication that happens only happens when needed, and every party only carries the data that it needs. So it's kind of like a complete partitioning of the model and the data at the same time. And when it's time, you update your model with your optimizer states, you get the new model parameters, and then you go for the next batch. And this is essentially the whole idea. Now you can use zero on its own as a data parallel approach in 3D parallelism. And this is the deep speed library. So you can have a data parallel using zero, and then each data parallel inside it, there is pipeline parallel, and each pipeline parallel has inside it model parallel. So you have the 3D parallelism with the zero optimization, which significantly improves the performance. And the way it works is like, okay, model parallelism has the largest communication overhead. So we prioritize placing the model parallel groups within a node to utilize the larger inter-node bandwidth. Then we have Megatron LM for tensor slicing that is happening inside here. And just exactly as I described, then we do the pipeline stages inside. Yeah, and then we see that with Zero, we basically combine all the benefits for all the approaches that we talked about. We get more than 1 trillion parameter model. We can do it. We can do parallelism to more than 1000x. We have very good compute efficiency, and the very good thing about Zero is that you really don't need to rewrite the code, because it is just an optimizer that you can apply in PyTorch. You can just use the deep speed library to do it for you. Yeah, and then you can see that you really need 3D parallelism in order to do stuff on the GPT-3 scale. For example, if you're doing model parallel equal 1, there's literally no way you can get any performance on a GPT-3 scale. You need at least model parallel equals 2 with very high pipeline parallel, and so on. You get the best kind of 3D parallelism is when the pipeline parallel is 20, model parallel is 2, and the data parallel is 20. The idea is that model parallel needs to be low for very high performance, because it's only used for memory efficiency. It's not used for performance gains, because it's not very efficient performance-wise if we're talking because of the communication overhead that it introduces. Yep, so these are my references. Thank you for listening, and I hope this was useful to you.